In this video, we're going to continue looking at the definitions required for doing psychrometric analysis, and we're going to particularly focus on dew point. So just as a reminder, from the last video, we had these definitions of the humidity ratio or specific humidity, sometimes called absolute humidity, but this is the mass of water vapor divided by the mass of air. And if you relate this to ideal gases, then we can estimate it using 0.622, which is really just the ratio of the molecular mass of water divided by the molecular mass of air, and then times the partial pressure of the water over the total pressure minus the partial pressure of the water. This would be the partial pressure of the air, in fact, in a binary mixture. The relative humidity is the mole fraction that's vapor divided by the mole fraction that would be vapor if the air were saturated with water. So this is the partial pressure of the water vapor divided by the partial pressure at saturation, which is equivalent to saying the partial pressure of, or the pressure that you would have if you were saturated water vapor. In our tables, saturated water vapor has a subscript G, so we'll use partial pressure subscript G to indicate that I'm going to be looking this up in the steam tables for saturated gas. The enthalpy of the moist air I can find using this definition. Now we want it on a per mass of dry air basis, and so therefore it's the specific enthalpy of the air plus the mass fraction of air per, or water per air, which is this absolute humidity or specific humidity, times the enthalpy of the water vapor. Again, I can approximate that by using the saturated vapor value out of the saturated water table. Next, let's talk about dew point temperature. Now, dew point, you hear this on a weather forecast all the time, so we all feel like we're familiar with this. But what it really means is it's the temperature that if I were to hold the pressure constant and cool my gas to this temperature, the water would just begin to condense. So I'd form that first drop of dew on the morning grass, for instance. Now, if the actual temperature and the dew point temperature are the same, this is an indication that you are saturated, so the relative humidity would be 100%. So let's just, to make sure we all understand this, consider a sample of moist air. Initially it's at state 1, which is right here on this chart. Okay, it's a superheated water vapor that's in air, and I want to cool it at a constant pressure. So if I have a TV diagram, then that means I'm going to follow a constant pressure line. And I'll do that until I reach the saturation curve. So the amount of water in the air is going to stay there because it's still superheated vapor until I reach saturation. Okay? So the partial pressure, being mole fraction times total pressure, will remain the same. But once it cools to point D, which is right here, following this constant pressure curve until I hit the saturation curve, that point right there, okay? At that moment, the water is going to condense, okay? So it's going to start to condense, but every time a little bit condenses, it's going to take some of the moles of water out of the air. So therefore, Y of the vapor, the water vapor, is going to decrease as I do this. And that's going to decrease the partial pressure of the water vapor, which means I'm going to change to a lower and lower point. Okay, now I'll have some liquid water at that same pressure, but I'll have this. So I'm going to come across here, and then I'm going to start sliding down the curve at lower and lower pressures because I have lower and lower mole fractions. Okay. The key thing is the amount of the dry air remains constant no matter what I'm doing with the liquid water, because the dry air is not condensing. So the mass that is vapor is going to be this specific humidity, mass of vapor per mass of air, times the mass of the dry air. This part is remaining constant. So as the water condenses, I can figure out how much is condensing by looking at this difference between the specific humidity at the beginning and at the end. And that will tell me how much per kilogram of dry air is going to condense. So next, let's look at an example. I have a mixture of helium and water, okay? Totally random mixture, but helium I know is a gas. It's not going to condense, and the water vapor is possibly going to condense. Right now it's at 80 degrees C and a pressure of 1.5 atmospheres, okay? So I've got water and vapor, or water vapor and helium in this condition here, where the water possibly is going to be a liquid, possibly is going to be a vapor, depending on exactly what the state is. Now in this particular case, it's all a gas, and it's 85% helium, it's 15% water at 80 degrees C and 1.5 atmospheres. Now I want to take this and I want to cool it at constant pressure and figure out what the temperature is where the water vapor is going to begin condensing. So, switching over to Excel for a moment, the idea is that the mole fraction of the water vapor is going to stay constant until the condensation begins. Okay? And the condensation is going to happen when the partial pressure reaches the vapor pressure. So if I can calculate the partial pressure by calculating the vapor pressure, I can figure out what that condition is going to be. So the partial pressure needs to be, well, 15% of 1.5 atmospheres. So 0.225 atmospheres. And I want to figure out what temperature this is going to occur at. Well, okay, I could go to a saturated water table and look for this as saturation pressure and interpolate to find the temperature. And that's not really a problem. It's not like that's a very hard thing to do, but I just want to introduce to you the Antoine equation and using that. The Antoine equation is a fairly well-established equation for calculating water, or actually any sort of material, but the vapor pressure curve relating temperature and vapor pressure. So in this case, in one of the textbooks that I use for a different course, this is the Antoine equation that they have, and for water we have this information. Now, the constants that are appropriate change depending on the temperature range. In this case, I'm talking about 80 degrees C, so I would like this second set of constants. Okay? I said that it was 0.225 atmospheres is the partial pressure of water, but this is going to give me a value in millimeters of mercury. So I changed that by noting that 760 millimeters of mercury is equal to 1 atmosphere of pressure. And so this is 171 millimeters of mercury is the partial pressure that I want. And so now I want to solve this equation for the temperature that will cause the partial pressure or the vapor pressure to be 171 millimeters of mercury. So using these constants and solving this algebraically for T, I was able to find that it was 62.9 degrees C. Now the most important thing that I really want you to see here is that I said this was helium. Did I ever use the fact that it was helium anywhere? No. All that really mattered, if this is an ideal gas mixture, all that mattered was the behavior of the water, because that was the one that was likely to condense. Any non-condensable carrier gas would have gotten the same value. Okay? So I could have used nitrogen here, or air, or argon, or methane, anything that is not likely to condense at temperatures near the operating conditions. So that concludes this video. In the next video, we will continue looking at psychrometrics, but we will start looking at the humidification charts.